linearly. My fear, and it would help me if you could remind me, if until I hit the record button, like none of that's going to show up on video. So if you want to be nice to the students that didn't come to lecture, or if you want to potentially hear all this again at some point, if you see I'm not recording, please remind me so that I'll hit that record button and make sure that I record what we're saying. So this is the start of Bayesian estimation. It's really nice. There's this idea that you've got prior domain knowledge, and we saw an example of that. There's a controversial history, but I'll say a little bit more about that shortly. And prior knowledge can be good as long as it's right. And we saw a maximum likelihood estimation example where we had a fixed parameter. I should start pointing there and start using the pointer here if I can find it. There it is. So we had a maximum likelihood example where we were trying to estimate a parameter that was fixed. This wasn't a random number, but it was an unknown parameter of a distribution that we were trying to estimate. And we did this by maximum likelihood. If you're not an expert in maximum likelihood or you haven't used it before, I tried to provide enough of an introduction that you could understand it. And we went through and did it, and saw that it gave us something that was very reasonable. And then we said, okay, and now what if I give you this additional information that X is bounded? And we thought, well, what would you naturally do as an engineer if you haven't gone through and really taken this class? How would you represent that, and what kind of estimator would you come up with? And we ended up with this natural estimator. And I sketched out what the PDF of that estimator might look like. And it turns out this estimator isn't optimal. And so we started talking about some of the drawbacks, how to model this as now a random variable, modeling this kind of engineering knowledge of knowing that X is bounded is taking on a uniform distribution over that same range. That's one way in which we can model this information that might be given to us in a practical application. And that brought us to the last slide that I think we covered, where we talked about a different error criterion, possible error criterion. This isn't the only one you could use, but the mean squared error in a Bayesian sense, which was very different than the mean squared error in the classical sense. In the classical sense, you're treating X as a parameter. It's not a random variable. So when you're calculating the mean squared error as some type of expectation, in the classical case, this expectation is only taken over the random variable Y, because that's the only thing that's random. X isn't random. But in the Bayesian framework, you're actually taking this expectation over the joint distribution of both X and Y. And so there end up being two integrals there instead of one. And that points us in a pretty different direction. We end up with a different optimal solution, and we end up with a really nice way of being able to balance prior information with what the data is telling us. And that'll be a fundamental kind of idea of the whole class and the state space methods, is that you've got prior information and you've got data. And this Bayesian framework brings those two together and enables you to combine them in a way that's optimal. And the optimality criterion, if you're estimating the mean, ends up being this expected mean squared error in the Bayesian sense. So the Bayesian mean squared error, for example, is one of the things that is most typically minimized. One other thing I'll point out, in this class, we're going to be dealing with a case where the thing we're trying to estimate is a vector. This is obviously the case where X is a scalar and where it's a real scalar, because I've used parentheses. This isn't a norm, and I'm just squaring it. I'm not taking the absolute value squared, which would handle the complex case. But be prepared when very shortly we're going to be talking about the vector case, and the notation is essentially going to be the same. So when we're talking about these probabilities, right now you're probably thinking of Y as a scalar and X as a scalar, but very soon those are going to become vectors, and you'll need to think of those as vectors. So usually the state is a vector, and we've got more than one measurement, so we put all the measurements together in a single vector. And we'll add time indices, which will complicate things further, and then later we'll add particle indices, which will complicate things even further. There's a lot of notation, but for now I was keeping it simple and doing the scalar case, but I just wanted to prepare you for that generalization that's coming. You guys with me? Yeah, it's okay. All right. So just to say a little bit more about the differences to help you understand the different framework. I've got the same model up here, but obviously I didn't use boldface to indicate what was random. So this is just kind of a generic diagram. But in the classical approach, again, the thing we're trying to estimate is some fixed but unknown parameter. We don't usually model that as a random variable when we're using classical estimation. And probably the most common type of classical estimation is maximum likelihood estimation, but there are other types where you could minimize mean squared error or other things as defined in the classical sense, where X is not random. The only thing that's random is the data that you're measuring that has some relationship to the thing that you're trying to estimate. So when you're thinking about performing an experiment where you get a different realization with each experiment, the thing we're trying to estimate doesn't change from one experiment to another in this classical sense. It's fixed, it's constant. So it's, for those of you that remember this from classes on probability or statistics, or with me a year ago with nonparametric estimation, the X is constant over the entire ensemble of all possible realizations. And one of the things that happens, I can't explain why this happens concisely, but one of the things that often happens in this classical framework is you end up with an optimal estimator depending on the thing you're trying to estimate. And for those of you that took nonparametric estimation a year ago, you saw an example of that where estimating, just as an example, estimating a confidence interval for an autocorrelation function ended up depending on what the real autocorrelation was. And so we had to finesse that and say, well, let's just look at the white noise case, and anything that's far enough away from white noise, we'll declare that as significant. So there was sort of a fudge there to make that work. But that was an example where we had an unknown autocorrelation that is not random, was fixed. And when we estimated it, when we came up with the optimal estimator, it depended on the actual autocorrelation, which was exactly the thing we were trying to estimate. So it's like, great, now what do I do with this? And that's kind of a hole that you often end up in with the classical approach when you're trying to do optimal estimation. With Bayesian estimation, you often get out of that. It usually doesn't depend on it never depends on what you're trying to estimate, because you model the thing you're trying to estimate as a random variable. It changes with each realization, and the ensemble includes values of both x and y. So over the ensemble, the thing you're trying to estimate is always changing, and that helps when you're going through and doing the math. Because basically I can't go back with this screencasting thing I'm using, but when you're doing the estimation, basically there's an expectation over x, and you're trying to optimize over that. And so when you do the math and take the derivatives, it ends up not depending on x because it's effectively integrated out. So for now, just take my word for it that you often end up with Bayesian framework. You often end up with estimators that are realizable. You get out of that hole. So that's a really nice property that they have. But being aware of this difference between the classical and the Bayesian approach is important, especially as you work with people that are familiar with the classical approach, and you're going to need to be able to articulate what those differences are. There's some notational weirdness and redundancy, or maybe I should call it overloading, in this class that you should be familiar with. In the classical case, once again, we're trying to estimate a deterministic parameter. We don't know what it is. You can think of it as like a mean of a distribution, as an example. Or if you took nonparametric estimation, you can think of it as maybe a power spectral density, or an autocorrelation function, or a cross-correlation function. But usually when we're talking about the PDF, as I've mentioned before, when the PDF depends on a parameter and you don't know what it is, notationally, the way this is usually represented is with a semicolon. So say the probability of some random variable y taken on a specific value y, and this PDF depends on some parameter or set of parameters x, and I just don't know what they are. And as I mentioned before, if you evaluate this function where the independent variable is x for a fixed value of y, if you take a measurement, plug it into this PDF, and then you're evaluating this as a function of x, then it takes on a different name. It's no longer a PDF, and in fact, it doesn't even have to integrate to have unit area. We'll see an example that doesn't later today or next Tuesday. But this function is called the likelihood function. And people, they're doing classical estimation, are often trying to find the maximum likelihood. Now, I bring this up not because we are going to be using that or that we really care, but to contrast it with something we are going to be working with. This is an unconditional PDF. This is not y given x. When you have that given notation, like I have down here, that given means given that you know what another random variable is. But this is not a random variable, it's a fixed parameter. And an example of that is if we say y is equal to some unknown mean plus v, where v takes on a normal distribution with 0 mean, then the PDF of y is also a normal distribution, and it has a mean mu and a variance sigma squared. And so those are two parameters of the distribution. So I've got, this is the probability of y, and this PDF is parameterized by both mu and sigma. But it's not given that you are told what those are. It is parameterized by those. And so that's how it's done in the classical case. The related idea in the Bayesian case is if x is a random variable rather than deterministic, then the PDF is represented as a conditional probability. This was an unconditional probability. It's parameterized by mu and sigma, but it's not conditioned on anything, whereas this one is a conditional probability. Eric?
Sorry, I guess I don't understand what we gain from changing notation from just saying y distributed as whatever probability of y to the semicolon notation.
You don't understand what we gain in going from...
Like the last line of the classical case, I understand the notation in that. That's sort of the notation that we always use to describe
conditional probability.
Yeah.
But the difference is that in the classical case, because you assume that it's not a random variable, it's constant, you don't get any extra information. But if I know one specific thing is, and I also know what its PDF is, I get more information. Because now I can say, not only do I know what x is, but since I know what its PDF is, I can use Bayes' theorem to get a more reduced PDF.
Okay.
Thank you. That was perfect. Yeah, that's exactly right. But the main point I was trying to get across in this slide is that we're dealing with something different when we talk about this conditional probability. But in the Bayesian literature, it has the same name. This is still called the likelihood function, even though it's really a conditional probability, the probability of y given x. And I'm going to use that term because it's convenient and because it's used in the literature. So I'm going to call this the likelihood, even though it really is this conditional probability, and it's related to but different than the likelihood function in the classical case. Yes?
I'm
sorry, remind me of your name?
Aaron.
Aaron, thank you.
Is there a convenient way to do random variable notation in handwriting? It's not bold-facing letters?
Yeah, I'm sorry, I don't think you have that advantage.
Just push
I don't know how to do it. Sorry, I don't know how to solve that notational problem with a pencil.
I was just wondering if there was a convention that was generally accepted.
Not that I'm aware of.
And you can use chalkboard bold. Just like write the letter twice on itself
Oh,
with
yeah.
an offset.
Bring a red pen.
Yeah, you could do it that way. In most cases, you can tell whether it's a random variable or not from context. And as soon as we get beyond this contrast between the classical and the Bayesian framework, we'll essentially always be working with random variables, so then it won't really matter that much. So again, this is a conditional PDF. It's not, in the classical case, it was unconditional. In the Bayesian framework, it's conditional. And if we have an analogous example where we say y is equal to some random variable x plus v, and now we look at the PDF, there's a joint PDF between y and x, but there's also this conditional PDF, the PDF of y conditioned on knowing x, or given that x takes on some particular value, and still parameterized by sigma. If you look at this, you're like, well, that looks very similar to this, and it is, but the difference is this is a case where we know what a random variable is taken on. We're given what its value is. And I haven't quite explained this yet, but Andy's intuition or knowledge was spot on in terms of when you condition this on X, the distribution often narrows, and you have a better idea of what Y is.
So does that mean when we're doing our Bayesian estimators, we need to have an idea of what the PDF of X is before we start?
Yeah, you will. And that will come. It turns out, again, I can't flip through these slides efficiently, but that will come from the process model.
Yeah.
So you've got those two equations, and basically the process model represents the prior knowledge. The measurement model represents what the data is telling you.
So in your previous case, your constraints gave you your prior PDF. Or is that something different?
Yeah, that's right. Right. We're not yet working with state space models. We will be soon. But when we are working with state space models, the prior comes directly from the process model. So it's not something you'll have to think up, but you will have to design a process model and then extract the prior PDF from it. I'll say more about that shortly.
Is that notation there with the, so it's actually a specific instance of X there that's in the PDF on the last two lines?
Yes. Oftentimes, this is written as the probability of Y given that the random variable X, it takes on a specific value X. And this is basically representing a shorthand notation of the same thing. I mean the same thing by that. This is just, if I wrote this everywhere, a big letter is equal to a small letter, where this is the random variable, and where this is the random variable, and this is the specific value it takes on, the notation would be really cumbersome. This slide, it would just be hard to see. But it does mean the same thing. Thanks for asking for that clarification.
So in this case, again, sorry to keep interrupting, but at the base there, where you're saying that X equals X, then you don't have any prior knowledge there, because if it was, it would change that from being just the normal distribution for the final PDF.
Andy, I'm sorry, I missed your question. What was it?
Yeah, in this case, because we don't have any prior information about X, we can't get a different PDF for the conditional probability, but if we did, it would change that stuff on the right, because you couldn't just say that they're equal.
Yeah, I didn't mean to imply that this joint PDF was equal to this. That's almost never the case. Yeah. All right. The main point of the slide was mostly about a difference in notation, and to especially overcome any confusion in using the word likelihood to mean two related but different ideas. That was the main thing of the course.
I'm a little confused why it's referred to as the likelihood function. Conditional probability of Y given a particular value of X is still referred to as the likelihood function. Since what's the different meaning of that? Because it doesn't encapsulate anymore the variation of the PDF for Y given any change in X.
Yeah, who came up with this convention? Why are they using the word likelihood? I don't know the answer to that.
What does it do in the Bayesian approach?
I'll get to that. Let me. I'll go. I think if we continue on, a lot of what you're asking will be clear. These are great questions, but it's kind of anticipating what's coming up. So why don't we work through an example, and I think this whole framework will become more clear to you. It'll take a while to work through this, but that's okay. It's worthwhile. So by Bayes' theorem, again, we've got these equations. Right now we're thinking of all these as scalars, but it also works when you're dealing with vectors. So basically I'm taking a joint probability and I'm breaking it up in two different ways. There's a probability of X conditioned on Y times the marginal of just the probability on Y, and then you can break this up the other way also, where this is equal to the probability of Y conditioned on X times the marginal probability of X. So we can start to use that right away. If we say, let's say we want to find an estimator that minimizes the mean squared error, the Bayesian mean squared error. If we substitute in this product for the joint probability here, then we can change the order of integration so that rather than integrating over Y first, we're integrating over X first. And so we've got kind of this inner integral that we can evaluate first. And one nice thing that happens about this is that because we're only trying to estimate what x hat is, and because this is positive for all values of y, if we can find the x that minimizes this, then it will also minimize this outer integral. If we can solve this for every particular value of y, then regardless of what value of y this takes on, it's also going to minimize the combination of both of these integrals. And so our problem becomes simpler of where we really just need to minimize this mean squared error in the inner brackets. And that will minimize the overall Bayesian mean squared error. Is that okay? All right. For those of you that are confused, you're like, well, I'm not so sure. I'm not persuaded of that. If you don't move your head, I see students nodding their head yes. I'm like, great, everyone gets it. It's a common mistake that we instructors make. So let's continue, though, because the punchline here is definitely solid and good. So when you're minimizing something, I haven't shown it here, but when you're minimizing something, you take the derivative, you set it to 0, and you find either a minima or a maxima. And in this case, I can just tell you that what we're finding is a minimum, and that there's only one minimum, and it's the global minimum. So I'm not proving that here. That's kind of missing from the idea that we're getting the minimum mean squared error estimator. But nonetheless, that's the approach I've sketched out here. It's easy to find on the web, or probably in some of the references I've provided, the other proof that there's only one minimum, and that this is finding that minimum and it's not finding a maximum. So setting those subtleties aside, if we take the derivative of that mean squared error, that term that was in the brackets on the previous slide, we're just taking the partial of this relative to x hat, the thing that we're trying to minimize over. And we can change the order here, where we can bring the partial inside the integral because it's a linear they're both linear operators, so the order doesn't matter. And the only thing that depends on x hat is this term. We take the derivative, and you get the derivative. We can then split this out into two separate integrals. All of you should be able to follow this calculus and algebra pretty easily. And if you look carefully at what we're left with on this line, this second term over here is just an integral of a probability over dx. And because this is a PDF, it always has an area of 1. And so this whole term goes away because it's just equal to 1. And so we're left with these terms, these two terms, this overall term and this term. If we set this whole thing equal to 0, because we're trying to find a minimum, then we end up with the expression down here at the bottom where x hat, you move this to the right-hand side, or I guess this over to the left-hand side, and divide both sides by 2, and you end up with this equation down here. I guess I can move this. And this, if you study it carefully, is really just the expected value of the random variable x, given that we know what y is, given that y takes on some particular value. Is that okay on the math? There was a little bit of sleight of hand there again where I was skipping over some of the details, but this isn't a math class. It's really an applied signal processing course, so I hope that's okay. So the main result of all that is that if we're looking for an estimator that minimizes the Bayesian mean squared error, the estimator that does that is the mean of the posterior, what's called the posterior PDF. So I'm introducing a new term, and I've put it in bold here, posterior. The reason this is called the posterior PDF is because it's after you've taken a measurement. It's after you've seen y. So once you know what y is, then you can consider this posterior PDF because it's conditioned on knowing y. So that's where the term posterior comes from. That's why they use that term. This posterior PDF ends up being the key thing fundamentally. It's not always framed this way, but all the state space methods are really trying to find the posterior PDF and do something with it. They represent the posterior PDF in very different forms. We'll see many different ways in which that can be represented, but fundamentally, they're all trying to get at the posterior PDF.
So Bayes' rule has that symmetry, right? You can flip it around.
Yeah, that's
all
right.
the time. Are you going to stick to a convention with notation between X and Y, which one's the posterior and which one's the likelihood?
I am.
Thank you.
You're welcome. Yeah, throughout this entire class, our measurements will always be in the vector y, and the thing we're trying to estimate, the state, will always be represented by x. And there's kind of one weird exception, but PDFs, I always represent with either a P, or we'll see there's something that's closely related that sometimes gets represented as a Q. We'll get to that a little bit later with particle filters. But other than that, whenever you see a P that is a function of something, you can count on that being a probability. So notationally, yeah, it'll be consistent throughout. Now this particular example where we arrived at the mean of the posterior was for minimizing the Bayesian mean squared error, but I've mentioned there's other types of errors you could consider. You could talk about a Bayesian mean absolute error or a Bayesian maximum error. And in those cases, you would end up with different types of estimators, but it would still all rely on this posterior distribution. The posterior distribution is going to be the key thing that you're going to want whenever you've got a tracking application. And again, there's many different ways of getting at that and representing that posterior, but it's the posterior. That's this whole class, in a way, is about finding that posterior distribution, some representation of that posterior distribution.
So going back before, if you wanted to minimize the mean absolute error, you take instead of taking the expectation, you take the median of the PDF.
Well, you take the mean absolute value, and the math gets a little bit complicated in terms of showing that the median minimizes that, but it does, at least in the scalar case. In the vector case, it gets more complicated. Okay, so we need the posterior, and no one's going to give it to you. Instead, they're going to give you hopefully a fat salary and ask you to go work and put your time into finding it. So so how do we go from the information that you're given to getting at this posterior? And you know, it's called Bayesian estimation for a reason. Bayes' rule is something that we'll be using over and over again. So one way of getting at the posterior, let's see, I'm going to get better and better at using this application. Great. One way of getting at the posterior is to use Bayes' rule and say, well, we know the posterior. Maybe I'll make a note because I didn't put it on the slides. This is the posterior. I should do that in a different color. The posterior can be written as a product of what we saw earlier is called the likelihood times this marginal probability. And this marginal probability will consistently be called the prior. This represents the prior knowledge that we have. Divided by this other term that I don't think has a word to describe it because it ends up being unimportant. And it's unimportant because it does not depend on x. Remember, we're trying to estimate x, and this probability down here only depends on y, which is known. So you can think of this as a constant. Once you get your measurement, you can plug that in, and that's just a constant. It doesn't really matter or help us much. Another way of thinking about that term is that it's just a factor that helps us ensure that when you integrate this probability, that it integrates to 1 the way that it should. So you can think of it as a normalizing factor just to ensure that this is a proper probability. But for our purposes, it's going to turn out that we often don't care. As long as we have a function or some representation that is proportional to this probability, it's going to be sufficient for our purposes, for estimating a mean or modes or whatever we want to do with it. But that's why this bottom term doesn't have a common name that is used. But you will hear me throughout this class talk about the posterior probability, the likelihood, and the prior. And what's coming is when we talk about the state space models, is the likelihood is something that you can usually get pretty easily from the measurement model, and the prior is something that you can usually get pretty easily from the process model. So those two equations that define state space models are what will give us those two probabilities that we need in the framework that we headed towards. I hope you guys don't mind that I'm mentioning what's coming. I'm kind of not foreshadowing, but talking about things we haven't quite gotten to yet. I hope you're not losing track of the kind of the simple example we're trying to work through. Do you guys have any questions yet?
Can you just repeat what you just said? You get the likelihood from the measurement model?
Yeah, correct. So let me try here. So I think this will work. So you may remember that earlier we had x of n is equal to some function of what the state was at time n and some noise that kind of perturbs the state. So the state at time n plus 1 just depends on those two things. The other equation is that we've got a set of measurements that has some relationship to the state vector that we're trying to estimate. But it's not a perfect deterministic relationship. There's some noise involved as well. And getting better and better at this. This equation here is often called the process model. Sometimes it's called the state model, but I'll usually refer to it as the process model. And this is usually called either the measurement model, I'll usually use that term, or sometimes it's called the observation model. So what we'll see in the next set of slides when we talk about optimal tracking is that the likelihood will come from the measurement model, and the prior will come from the process model. So that's coming. We're not there yet, but that's part of the reason that I'm going through these equations slowly and showing you everything here. Any other questions? Yeah, Andy?
Is there a reason you don't include a feed-through term in the measurement model?
You know what? You could generalize it so that there's something else that you can see that goes through also. In most signal processing applications, you don't have that external known inputs, but it doesn't actually change any of the math that's coming in. In fact, you could just integrate that into saying that's part of the definition of f of n and h of n, is that these are time varying, and they're partly time varying because you've got these other inputs that change them. So it's pretty easy to incorporate that if you've got a case where there's a known input. This noise and this noise are usually things that we assume we can't observe. We may know what their statistical properties are, what their distributions are, but they're random variables that we usually can't observe directly. But if you've got observed inputs that come into your system, either into your process model or into your measurement model, those are really easy to account for. Got controls people here. All right, so let's go through a Bayesian estimation example that's very similar to the classical estimation example that we worked through earlier. So this looks the same. In fact, I just copied the same diagram. I didn't go through the trouble of making all these letters or the X letter bold this time in the diagram. So it's the same diagram. The key difference is, though, that we're adding now a random variable X in our model. And, I want to emphasize that in the textbooks for classes like this, they'll often start by giving you equations like this and then say, okay, go through and do the math, turn the crank, and solve it. But as practicing engineers, you have to take kind of a problem context and think about how you're going to model it. In practice, you have to come up with this and say, well, it's reasonable to model that noise as additive noise for this reason. And I've collected data, and I've analyzed the distribution, and it appears to be normally distributed. And I've also looked at the correlation properties and the power spectral density, and it seems to be uncorrelated. Maybe it's not statistically independent, but at least it looks uncorrelated. You have to go through and do that work and really create these models. So it's a little bit of a cheat to start off by saying, let's assume, and you've got all this, and now you've just got to do the math. In practice, there's much more to be done than just the math. You often have to develop the model. I'll talk more about model design a little bit later in this term, or modeling processes. So y is equal to x plus v. We can also write v is equal to y minus x, and we're told that the measurement noise it can be modeled as having a normal distribution with zero mean and some variant sigma squared that's given. So, and you know, we often do this in the state space framework as well, where we often have a measurement model where there's usually a nonlinear function of the state, but then we often have additive measurement noise. And because of the central limit theorem, for those of you that are familiar with it, often it's reasonable to model that noise with a normal distribution. But not always. It's a good idea to characterize it. So if we know what x is, then y is going to have the same distribution as v, but with a shifted mean, because we're just adding now, basically we're just adding a constant to a random variable with a known distribution. So there's a couple of different ways that you can arrive at the main point down here, but do you mind closing the door? Thank you. And I'm sorry, remind me, your first name is? Fu. I thought it was. Okay, good. Yeah, thanks. So the PDF of y then can basically be written as the same as a PDF of v, but with a shifted mean. So this also, it turns out, the conditional PDF of y given x, the likelihood in this case, is just also a normal distribution, but now with a mean equal to x. And that's going to be true in the vector case. This is something that we often use when we're modeling a state space process, and we have to go from a measurement model, which is given by this equation. This is probably the simplest of measurement models. The measurement is simply the state plus some measurement noise. So this is the state. You can think of this as the state plus measurement noise, and that gives us our measurement. And then one of the things we need, the likelihood, which is right here, ends up being just a normal distribution with a mean of whatever the state happened to be. This is conditioned on knowing the state, so there's nothing wrong with that. But that's how we make that jump from measurement model to likelihood that I'd mentioned before, or at least one way that you can do it. Yeah? Okay. All right. The other thing that we had decided before is that we said, okay, we've got this prior knowledge that x is bounded, and it's going to be in the range of some x min to x max. You know, so that was our prior knowledge. So, okay, we're going to model that with a uniform distribution, uniform prior distribution. Well, the thing that we need is the posterior. The posterior is equal to the likelihood times the prior divided by this normalizing factor that we usually don't care about. We now know what our likelihood function is. We derived that on the previous slide. We figured out what our prior was actually on Tuesday, and we said this is going to be a uniform distribution, and we just multiply those two together and divide it by this. We don't actually know what the probability of y is when it's not conditioned on x, but we do know that this can be written as the integral of this product, and we know what both those terms are because they're identical to what's in the numerator. So if you did want that normalizing factor in there, it's just basically the integral of the numerator over x. So we've got it all. Here it is. Here's the math, you know, and it's in symbolic form. It works for any variance, any measured value of y, and of course any x max or x min. Now I wrote this, you know, got this curly brace because when you multiply these two together, this is only 1 over x max minus x min over this range when x is within that range. When x is outside of that range, this prior probability is equal to 0. And so, you know, the probability of x given y is equal to all of this only over that range. Outside of that range, it's equal to 0. Is that okay? So there it is. For the simple example, that's it. And again, you can write this as, you'll see this symbol sometimes in my slides. You may not be familiar with it. Whenever you see that symbol, it means proportional to. So within, you know, this, the left side is equal to the right side within a scaling constant. They may differ by some scale factor, but otherwise this is proportional to that. So that just simplifies the notation a little bit, is all that does. I'm sorry, you know, if I had to, I think there's a way that I can like duplicate the slide and move it forward or something. Do you want me to go back?
No, it's okay.
It's okay? Okay. All right. This is really cool, I think. So this is our prior PDF. If you didn't have any information, you're just told x is somewhere between 1 and 3. You know, I said x min equal to 1 and x max is equal to 3. I pretended that we got a measurement, and that measurement ended up being 3, and I must have chosen a sigma of 1. And if you had no information, if you had no measurements, then your best guess, if you want to minimize mean squared error, would simply be at the middle of your range between 3 and 1. In the absence of any other information, then you basically say all values are equally probable. And if you want to minimize mean squared error, you go right to the middle. And the vertical line shows the mean. So based on the prior alone, we would guess, if we want to minimize mean squared error, we would guess 2. If we didn't know anything about these constraints, and we were just doing classical estimation, and we did maximum likelihood, and this, by the way, well, this is the probability of y given x, so this is the likelihood. But it's plotted as a function of x. So the way I'm plotting this is for a fixed value of y equal to 3, and I'm plotting this as a function of x. So although it looks like a PDF, it doesn't have the property of a PDF. It doesn't have to have unit area. It happens to in this example, but in general, the likelihood function is not a PDF. And if you integrate it, it usually doesn't have an area of 1. It just happens to in this example. I'll show you an example later where that doesn't happen. But this is the likelihood. And the red line on this plot is showing where the maximum of the likelihood function is. So if we were doing classical estimation, or if we didn't have this prior information, then we would say, okay, well, we got a measurement of 3, and y is equal to x plus some noise that has a mean of 0. So you would then guess that the best value of x is what your measurement was. You would guess that it was 3. That would be the right thing to do if you want to minimize the mean squared error, or pretty much any other error because it's a symmetric distribution. But then we get to the Bayesian case, and the Bayesian is weighing these two extremes. It's accounting for both the prior information and the likelihood, and we end up with a posterior PDF, the thing that we're after, and it looks weird. And it's not like what we would have guessed when we were talking about what the natural estimator would be. Earlier we said, well, you know, most engineers that haven't taken this class or don't have any training in this would say, well, if y ends up being outside of the range, then you just set it equal to the maximum value. And so we ended up with a PDF that had 2 impulse functions, and otherwise looked like the likelihood function. So this was kind of the natural estimator PDF. But the Bayesian estimator is the mean of this posterior probability, and it looks different. You know, it's actually unlikely that you would get an estimate of 3, or that you would get an estimate of 1 in this case. You know, it doesn't have these impulse functions, but that's what the posterior looks like, and the mean is right in between the 3 and the 2 that were in the prior and that were in the likelihood. Go ahead.
I was just going to say, it just looks a lot like the product of the prior and the CDF of the likelihood, right? Which is exactly what we know it is from the previous equation.
Yeah, this is proportional to the product of those two. That's right. That's right. But you know, I'm speculating that you didn't know to multiply those two or to think about taking the mean of the posterior. But yeah, I mean, if you're following math, you're like, well, of course that's what you're going to get. You couldn't have gotten anything else. That's true.
Yeah.
That's true.
You said earlier that the likelihood here, the Bayesian likelihood, isn't a PDF, but isn't the Bayesian likelihood just another name for the conditional PDF? Right? So I mean, I can understand us not needing to scale it because we don't care about scale anyways at the end, but strictly speaking, isn't the Bayesian likelihood also a PDF?
It depends. It's a great question. And I'll rotate it so that we can see it. So the so-called likelihood, the probability of y given x, for a fixed value of y is not a PDF. If you're evaluating this where the independent variable is x, and you say, well, if for a fixed value of y, if I integrate this thing over x, does it have unit area? It doesn't have to. Happens to in this case, but usually it doesn't. But if you look at it the other way and you say, well, given that I know what x is, if I don't treat x as a variable, as the independent variable, but I fix x and then I evaluate this over y, then yeah, it's absolutely a PDF. So it depends on how you're looking at it. In our context, y is the measurement vector, and that's data that we actually have. I mean, we're usually getting that from sensors. And so y is usually the thing that's known, and x is the thing that's unknown that we're trying to estimate. So in our context, we're usually looking at this where it's some function of x for a known value of y. And in that situation, again, it's not a PDF. Yeah? Right. So, go through and do the math, and the expected value is just equal to the integral, the posterior times x, pretty standard. If you go through and you do the math, you say, okay, well, I'm going to apply that. The bottom term on the previous two slides back, was all just a constant. It actually didn't depend on x, so it falls outside of the integral. This stuff can be pulled outside of the integral because it doesn't depend on the variable of integration. And these two terms, of course, cancel, and it simplifies a little bit to this, where we've got a ratio of two integrals. And the only difference between these integrals is one has x and one doesn't, but you can't cancel anything further. I mean, that has x and that doesn't, and you can't really go any further. This is something that kind of can come up in Bayesian estimation, where you're like, well, now what? I can't. There's not a closed form solution for either of those integrals, and what do you do now? The good thing is, I had to update the slide, but it's 2016, not 1989, and it's really easy to do a numerical integration. That was how I arrived at each of these, well, at least this red line and this red line. This one, of course, I knew what it was. But for this one, I didn't really know what the mean was, but it's really easy and fast to compute that now. At least in this example. And this will be really interesting, especially for the next topic, because we can perform this integral very quickly, very easily. You can probably do it on your phones and pretty soon probably on your watches. But what you probably aren't going to be able to do is the case where this becomes multidimensional. That's where this starts to break down. When you try to evaluate multidimensional integrals numerically, you run into this thing called the curse of dimensionality, and we'll be talking a lot about that. So I say, will this work for state space tracking? And the answer here is sort of. It's sort of because of that issue. I'll say a lot more about that. Are you seeing if it's locked? Yeah, I don't think we can quiet those guys down. Yes?
No, I think he was first.
Can you go over again the meaning of the red lines on those graphs there, and I guess why especially the one on the posterior PDF?
Yeah.
I didn't quite catch where
Okay.
that was from or why
So
that's-
this is the mean of that distribution.
Right.
And if you didn't have any measurements, this is what you guess. Because all you know is that x is bounded. It can't be any larger than 3, and it can't be any less than 1. We get a measurement, and the measurement is 3. And if we were doing just maximum likelihood or classical estimation, we would pick the peak of that function, and we'd end up with an estimate that is 3. And the cute thing about Bayesian estimation is it weighs this competing information. You've got kind of conflicting information in a way. Your prior information says, it's over here, and now your measurement is saying it's over here. And the Bayesian estimator ended up, the optimal Bayesian estimator ended up placing it at about 2.3. That's the mean of the posterior. And the mean of the posterior is usually what we're after when we're doing state space tracking. Unless it's multimodal and you want to track a mode or pick a mode or you're worried about outliers or something else. But in most cases, most of the tracking algorithms are trying to find the mean of the posterior. You've all probably at least heard of the Kalman filter. And the Kalman filter is trying to estimate the mean of the posterior PDF.
So can we just keep playing the game forward, and like if we got another measurement and it's 2, then that would just update the posterior PDF?
Well, it's not. Unfortunately, it's not quite that simple. In this context so far, I don't have a time index,
Right.
and we don't have any notion about anything changing over time yet.
Okay.
So if you had a second measurement, now y would become a vector with 2 elements in it.
Right.
And so now you would have, this would be a little bit more complicated because you'd have to go through and do the math, but it becomes more complicated. It then depends, well, and those 2 measurements, are they related? Can you say that the noise is independent, or is there some correlation in the noise? If there's correlation in the noise, then those 2 measurements also are related, so you have to think about a joint PDF over both measurements that you took. If they're statistically independent, then the probabilities can be written as a product of the marginal probabilities. So there's all sorts of subtleties that come in. It's not quite as simple as you would hope. Yeah. Any other questions on this example? And we spent a long time on it, but we're hitting on key ideas of Bayesian estimation. And I think this is a really nice example for showing how you have prior information that is competing with essentially measurements, with data that's coming in, measurements that we're usually taking from sensors, being the engineers that we are. And when you've got that competing information where you say, I've got this prior knowledge that the thing I'm trying to estimate is usually over here, but now I've gotten a measurement and it says it's over there. And rather than you having to make a judgment, the nice thing about the Bayesian framework is it can figure out how to optimally combine that competing information into a single estimate of what it is that you're trying to estimate. And we'll talk more about how it does that and how it gives relative weighting to the prior information versus the likelihood versus the measurement data. We'll talk about that after our break. I think this is probably a good time to take a break. We've been at it for an hour. So let's take 5 minutes, and then we'll talk a little bit more about some of these ideas.
We're going to move on to the...
We're off. You guys ready? All right. So when you're looking at this equation in this particular example that illustrates a lot of the general ideas of Bayesian estimation, one of the things that you'll want to observe is that our estimator, x hat, is a function both of our measurement, y. You can only calculate what this x hat is, this posterior mean, if you know what the measurement data is. So it's a function of that, and it's also a function of the prior knowledge of x max and x min. You have to have all that. You have to have both bits of information in order to calculate the estimator. So again, this idea that it's weighting the observed data, the measurements that we can take, along with this prior knowledge is really the key idea of Bayesian estimation. And the estimator that minimizes the Bayesian mean squared error is not merely our measurement, as it would have been in the classical case, except for when x min goes to minus infinity and x max goes to positive infinity. It's called there's a name for this. It's called a uniform prior. And sometimes Bayesians, people who really like Bayesian estimation, will say that classical estimation is really also Bayesian estimation, but it's just the special case when they say that you've got a uniform distribution for all possible values that whatever it is you're trying to estimate can take on. I guess this may not be obvious at first, but keep in mind that this is expected value of x, where this is a normal distribution that has a mean of y. And so the expected value of a normal distribution is, of course, its mean, and the mean is y. And so if x min and x max, if those stretch out to positive infinity and negative infinity, then you're just taking the expected value of a normal distribution with a mean of y, so the mean will be y. So in this case, if we say you know what, we thought we had prior information, and we thought it was bounded between xmin and xmax, but really we've got no idea. So if you sort of discard your prior information, or if you say, my prior information is very broad, it stretches out over a very large range, then all the weight lands on your measurement, on the observed data, and it essentially kind of reverts back to being a classical type of estimation. So, you know, part of the magic of Bayesian estimation is not just that that it's able to integrate measurements with prior knowledge, but it also knows how to weight those two. And now you're starting to get a glimpse of how it weights those two. The less good our prior information is, the broader the range over which we say X can take on values, the more that the Bayesian estimate really relies on the measurement data and becomes closer to the classical estimate, the more it weights that measurement data. On the other hand, if we made this really tight, and you said, you know, we don't know exactly what X is, but it's between 1.1 and 1.2, then very little relative weight would be given to the measurement. If the measurement was 3, you know, the estimate isn't going to be outside this range of xmin to xmax, and it would effectively discard that measurement because we had really good prior information in that example.
Hopefully good.
Yeah, right. Yeah, if your prior is bad, you're hosed. I mean, that's your job, not my job, to have a good prior. I'm just teaching you what to do with it once you've got it. So the estimator is one way of thinking about this is that we're deliberately introducing bias. You know, classical estimators or people that do classical estimation would say, you know, this bias can be bad. And Walt raises a good point. You know, that it's good, that prior is good as long as it's accurate. And that's important because the estimator is biased towards the mean of the prior PDF. It's biased towards that prior knowledge we have. And that's good if that information's right, and it's bad if that information's wrong. Again, that's your job, not mine. And the effect of observing Y, basically the estimator ends up positioning it between the mean of the prior and the posterior mean. So, and again, part of the reason that we're going through all this is because as graduate students, getting a master's degree or getting a PhD, we often reach for some form of optimality. And in this sense, this Bayesian estimate minimizes the Bayesian mean squared error. So there's an optimality criterion by which we can say it's optimal by this criterion. And that's usually a good thing, especially when you're writing a paper or defending a thesis or a PhD. So the other thing you should think about, I encourage you to think about what happens as these limits, get wider or narrower and how that affects the estimator. You should also start to think about what happens when you have more noise or less noise. In most practical applications, you're taking measurements. Those measurements are often poor. And we model how good or how bad they are with the noise variance. So if you've got an instrument that's really bad, if you've got a lot of quantization error, if you've got a sensor that's really cheap and it doesn't measure things very accurately, then you may model that as though it has a very large variance. And conversely, if you've got a great, beautiful instrument, you know, very little quantization error, the engineers have really done a great job in designing a beautiful instrument that has very, very little noise, then you would model that as though it has a very low noise variance. And so you should think about what happens to the Bayesian estimate as your noise variance goes to 0 and you sort of go towards perfection in terms of your measurement. And conversely, what happens when your noise gets so large that you're basically ignoring the measurements altogether. And as the variance goes to 0, the posterior PDF becomes more and more concentrated at Y. And so the estimate will approach Y. This is kind of an extreme example because we've got a hard constraint on our prior of it can't go beyond xmin and xmax. Usually the prior is also a normal distribution or something else that has tails. And so usually this will be true. In this case, it would go as far as it could. But in any case, generally this is true. the less noise you have, the more the measurements are going to be weighted in estimating your state or the thing that you're interested in. And conversely, as you get more and more noise, it starts to go to just using the prior and using the prior estimate. So in this case, the Bayesian estimate would start to go towards just the expected value of x based on the prior alone, without accounting for the measurements at all. And I've got an example of that, I think, on the next slide. So in this case, I used the same limits of 1 and 3, but I changed the noise variance. So in one case, the noise variance was 1/3. In another case, it was 3. And I didn't plot the likelihood here. So I've just got the priors and the posteriors. And you can see when noise variance went down from, I think it was 1 initially, so I cut it by a factor of 3, or at least the standard deviation by a factor of 3. Now the Bayesian estimate is closer to 3, closer to where that measurement is. You know, we can rely on that measurement more because there's less noise. It's more trustworthy. We've got better information now that we've got less noise variance about where the thing is that we're trying to estimate, where it actually is. And so appropriately, the Bayesian estimator nudges that and moves that closer to 3. It weights this prior information less and weights the measurement much more. Conversely, when we add more noise, when we increase the noise sigma, the standard deviation of the noise by a factor of 3, now it's effectively ignoring the measurement. It says, you know, you told me that you got a measurement of 3 and that's basically the thing I'm trying to estimate, but the standard deviation is so large that the prior information is much better, and so it relies much more on that prior information. So that should start to give you a sense of what the effect is of the noise variance. The noisier it is, the more it relies on the prior.
Does the noise variance have to be finite, or can I have like a Cauchy distribution for my noise?
Generally, in this framework, we're not confined to distributions that have finite variance. This example is with a normal distribution, but we could have done this example with the noise having any distribution we wanted to. Everything would have worked out the same. We're not estimating the variance as any part of this, and so we don't run into any problem in working with more general distribution. That's one of the really nice things about particle filters and the Bayesian framework is there's no constraints, no assumptions of, we've got to assume the central limit theorem holds and that the noise is Gaussian. I used Gaussian noise in this example, but I didn't have to. It wouldn't have changed anything. That was a great question. Anything else on this so far? You guys kind of following? Yeah? All right. So just to reiterate some of the main points. This was a very simple example, and we spent a lot of time on it because it really conveyed a lot of the main ideas that are true in general for Bayesian estimation. Again, random variable, we're now modeling what we're estimating as a random variable. There's got to be this prior PDF to use this Bayesian framework, and in our context that will come from the process model. If you don't know anything, if you really don't have any prior information, you can still use the Bayesian framework and just have a uniform prior over a very large range. When that range becomes essentially infinite, it sort of reverts to classical estimation. So it's a very general framework. Once the data is observed, everything comes down to this posterior. We're going to be after the posterior when we're talking about the Kalman filter or the state space tracking. And the optimal estimator, one way of defining it is the estimate that minimizes the Bayesian mean squared error. And it's important to realize, and you'll see some examples of this, that this framework is trying to minimize the error over all realizations. So it's trying to be right on average. It may not produce the best estimate for your particular realization. It's trying to minimize the error over the entire ensemble. You know, it's this expectation over that joint distribution. So that's something to bear in mind, is it's trying to be right on average. It may not be right in your particular case. And it's always true when you're working with random variables, or usually true. I think we covered everything else. The estimator will be biased towards the prior. The part of your job as engineers doing signal processing is going to be developing a good prior that represents the knowledge that you actually have about the thing that you're trying to estimate. Because we're doing state space modeling, this will often be in the form of the dynamics to make sure that the dynamics accurately model whatever it is that you're trying to track. When you're talking about mechanical systems or physical systems, this is a little bit more straightforward. If you're talking about modeling a submarine going through the ocean that you're picking up with radar, where your measurements are the radar pings, and the state is basically the dynamic state of the submarine, its inertial state, then you may have a lot of knowledge about how that submarine can move, that it can only go so fast, it can only accelerate so fast, it can only turn so fast, dive so fast. But getting that part right is where a lot of the engineering is in this framework, is in designing that prior model. And it's hard to give good guidance on that because that often comes down to physics and is very specific to the application you're working on. There are some very general models that are used in a lot of applications, and we'll talk about those, but in many cases it comes down to your application. And as Walt pointed out, if if you don't get that right, then the prior can actually make things worse. I mean, the prior has to be accurate, or you could make things worse.
Is there a good way to test your prior? Like, is there a good way to test your prior?
One of the topics that's usually overlooked in the textbooks and in courses like this is how to tune the tracking algorithm. It's nice to say you've got beautiful theory, and if someone gives you a state space model, it's like, oh, you just turn the crank and you get the estimate and everything works. But in practice, there are often parts of the model where you just don't know. Like, well, I don't know what the process noise is. I mean, I made up that model, and maybe I got it wrong, so how do I evaluate that? And the short answer is it's going to come down to looking at how your prediction of the measurements differs from what the actual measurements are, because that's based on the state. And if you make a mistake in your modeling, that's the best indicator that you've gotten something wrong and that you're not tracking well. I'll say more about that later, but what it's going to come down to at a high level is you've got your actual measurement, and then you have an estimate of what your measurement is. And when you look at that difference on average should be a white noise process, and that's the best indicator as to whether you've got your model right and whether it's well tuned or not. We will talk more about that later. It's a really important topic. Again, there's some controversy about this. I joked last time that you wouldn't want me to grade as a Bayesian. That if I had prior impressions about all of you, and whether you're an A student or a B student, that you probably wouldn't want me applying that prior information here in calculating what your grade is. You'd probably want that to be a maximum likelihood estimate. And that kind of gets at the root of the controversy around this. And I'm just mentioning this in passing, but if you wander over to the statistics department, these days most statisticians will say, oh, sometimes the Bayesian is the right thing to do, sometimes classical is the right thing to do. But there used to be a debate between these two schools of thought. And those that were defending classical estimation were basically defending that you should listen to your data and let it speak for itself. You should not bias it towards what you think it ought to be. And the example of grading is a good example of an application where that would be the wrong thing to do. But as engineers, if we're tracking a submarine, you can do it much more accurately if you take account of how you think that submarine can move, or whale, or truck, or whatever it is. So in our context, this is often a very valuable thing to do. But again, you've got to get that prior knowledge right. And I will say a lot more about modeling and give you some examples as we go through the term. One problem that we came up with, or that we ran into, is that although we got an expression for the estimator, it included an integral, and evaluating that integral required numerical integration. And I mentioned this earlier, but as soon as you go to higher dimensions, numerical integration becomes a nightmare. Even if you know what the function is, you just quickly run out of cycles. I don't care how fast your processor is and how many cores you have. You can't go very high in dimension. This has a horrible exponential scaling property to it. And I'll say a lot more about that later. But when you think about the dimensions of what we're typically going to be estimating, where we've got the state vector, and even in the case of a submarine, you've got, if you're talking about its spatial position, you've got X, Y, and Z, and you're probably going to be tracking its velocity and maybe its acceleration, maybe its orientation. So, we're getting up into dimensions that are on the order of 8, 10, 20. And when you're in that high of dimensional space, numerical integration is just off the table. You simply can't do it. So that's one thing that we're going to run into, that we're going to have to overcome. The computation is just too bad for that case. And that's where particle filters have a bit of magic embedded in them that have a very tricky way of overcoming that limitation. So we'll talk about optimal estimation next, but we'll see that although it's perfect in one dimension, maybe even 2 or 3 dimensions, you can't go much higher than that. And that will lead us to particle filters. So this is a little bit more about what's coming ahead. And that's it for that set of slides. Do you guys have any questions about anything we talked about? Colin?
You say that, the probability of x given y integrated over x is 1.
Let me write that out. The probability of, say it again?
Of x given y, that all integrated over x.
Yes.
Yes?
Yes.
But if it's a likelihood function where x is known and y is unknown, then it becomes, and you're integrating over y. That's not equal to 1.
But this actually isn't, this is still the posterior. Where that came up was when we were talking about the likelihood function, the probability of y given x. Because usually we're evaluating things as a function of x. And if you integrate this as a function of x, then it's the same thing. In general, this is not equal to 1. It happened to be in the one example we worked through, but in general it won't be.
So for that top one, if it were just the probability of x integrated over x, that's also 1.
Correct. It's a PDF.
Just seems strange to me because if
All it's saying is x has to be something, right? You're looking at all possible values of x. It's gotta be 1.
okay, I'll think about that.
Don't quite believe it yet. We will see an example in the next set of slides where there's a likelihood function that doesn't have unit area. In fact, its area isn't even finite. So it's coming.
Can you say, like, if you have a probability where, if x is between 1 and 10, right, you have some sort of distribution of probability in there. And I can say, well, given y, and somehow that limits it between 1 and 5, you still have some probability that sums to 1, that it's between 1 and 5.
I'll cover it. Don't worry, we'll see an example. We'll come back to that. Any other questions about what we discussed in this set of slides? Bayesian framework, Bayesian estimation theory, modes, thinking about multimodal distributions, posterior distributions. Anything else? Okay.
So that whole posterior concept is important because it means that you've measured it, you have to make the measurement first, and then you get your state estimate. So
You'll have a much better estimate if you do that. That's right. Okay, great.